The idea is that it's 1 hour for lecturer who deliver a lecture, and then everybody welcome to discuss, to get question and so on. So this is a forum. So, so the idea is so your presentation, Alex, your presentation with 1 hour is great.
Actually, I will ask many questions in my presentation. I thought that because this is for the cover book, so I will push on you a number of
that's exactly what we're looking for.
Can you enable me to share screen, Ilya? You are the host? Sorry for I interrupted you. I tried to share screen, but it doesn't allow me as of now.
One moment. And now trying again.
Okay. Yeah, I think now it allows me. Let me see. Okay, you see my slides now?
Yes.
Okay, very good.
You see them as a full, or I should do something to get them to a full screen? You see only the slides, or you see above it also?
We see above it also, yeah. If you can make full screen.
It's probably not the optimal way. It's let's see. I always forget what to do. Okay, but it's maybe it's not so up. I did something wrong now. You still see it, or you lost it?
Yeah, we see your we don't see slides now. We see your other screen.
Now.
Yeah.
Just a second. Okay, so what did I do? Here it is. Just a second. Somehow I lost it. Just a second. I'll get it back.
Take your time. People are still coming.
Now you see it. I remember that there is something. There is no young people now to tell me what to do. Young people always know how to do this, and I gave so many talks, and still
I'm not young, but I think I can tell you what to do.
Oh, okay. So what should I do?
Open up that PDF again.
Okay, just a second. Just a second. You use PDF again. Okay. Now
open with at the top.
What to do?
At the top of the page in the middle, it says open with.
Open with. Okay, yeah.
And maybe open with the PDF one.
Open with this looming PDF.
Hang on. No.
Yep.
No, that would download. Okay, you don't have any PDF reader on your computer.
And I don't have PDF.
No, okay.
I'm back now. Anyway, so maybe. Okay.
Well, you can download it, and then so you, on the right-hand side, you've got a not that one.
Let's not download.
Okay, that's not.
You're complicated.
Just a moment. Now it's okay. Now you see the.
Yeah, that's okay.
It's okay. Okay. So you see all the garbage at the top, but that's okay. There are no secrets. Okay. Let's see. How can I arrange? What should I do that I will see some of you without seeing any face? Okay. Okay, I'm ready.
Very good. So shall we start?
I mean,
Or we wait a few more minutes? I don't know.
oh, somebody wrote
Yeah,
I think we can start.
F11.
somebody wrote
Let's F11. Somebody suggests.
with no control, just F11 or some control F11. Control. Okay, doesn't matter. I mean, it's okay. Better not to try to improve and then destroy. Right. Okay.
Maybe Alex, one more thing. Can you try to go one slide forward to see if it works?
Okay.
And then back.
Yeah.
You will have to scroll it this way.
But I put the wrong lecture. Oh, sorry. Actually, this is a better lecture, but more exciting about something new. But for you, I think you want to have this one because this has more group theory and more open problems. I'm sorry.
More group theory today. Yeah.
So now you see it, right? Stability and testability.
Yeah.
They are sort of related. Maybe I'll say one sentence about the other lecture to make you.
So and now how do you scroll?
Okay. Yeah, I think there's
you scroll it this way.
Yeah, okay. Yeah, okay, good.
All right, shall we start?
I'm fine, yeah.
Ilya, yeah. Okay, ready. Oh, everybody, welcome to the first meeting of Akademgorodok Forum this year. It's my great pleasure to introduce the speaker, Professor Alex Lubotzky from the Hebrew University in Jerusalem and Weizmann Institute. Let me just say a few words about Alex, whom we all know very well. I personally first met Alex in 1999 in Jerusalem. When I was a PhD student in Novosibirsk, I came to a conference in Israel together with my advisor, Alexander Dmitrievich Mednych, and Alexander Dmitrievich introduced me to Professor Lubotzky. That was a long time ago. Much later, we did some work together, which is not related to today's Alex talk. In fact, he has numerous contributions to group theory and its various applications, which greatly opened the horizons of applications and group theory. Today's talk is about stability and testability of permutation equations. Let me say that if you feel like asking questions, you can ask in chat or raise your hand and ask Alex during the talk. And then after the talk, if it's necessary, I will moderate the discussion, but please feel free to interrupt and ask your questions. Welcome, Alex.
Thank you very much. And I'm grateful to the opportunity, and I also should grateful backwards to the people who initiated the legendary book of open problems in group theory. I kind of grew up on that book, and I remember as a young student or young, I don't remember, I think even when I was student, when exactly it was started?
Oh, it was before me, before my time.
Years ago, I was kind of going on the pages and look for a problem that maybe I can solve. Usually without finding such one, but over the years, maybe some a few. But
started in 1965.
Oh, okay. So yeah, so even when I was a student, right? 65, I was 9 years old, so I was okay. You are really modern in spirit, and to understand that nowadays you can use also the technology to have also an international seminar like that, and not just that. So actually, I chose this subject, which is kind of a new perspective. I mean, some of the problems you will see are maybe old, but in the last couple of years, few of us gave it maybe a little bit of a new flavor. And I want to try to make the group theory community interested in this type of problems. Some of them related to some old problems, I will mention it. And some of them I think are kind of new, but natural and interesting. So for me, the starting point of all this was a paper I came pretty accidentally. I saw the following paper by Gulnara Arjasteva and Vilio Nesco few years ago, and they proved the following theorem. Let's read it slowly and carefully. They proved that for every epsilon greater than 0, there exists delta greater than 0, so that if you take two permutations, A and B, in the symmetric group that satisfy the distance of the commutator from the identity is less than delta. We'll say in a minute what does it mean. Then there exists A prime and B prime in the symmetric group, in the same symmetric group sim n, such that the distance of A prime from A and the distance from B prime of B is very small, is less than epsilon, and the commutator of A prime and B prime is exactly 1. Namely, let me skip this line and go to this line. If two permutations nearly commute, then they are near permutation that truly commute. If you take two permutations whose commutator is nearby the identity, then you can deform them, each one of them just a little bit, so that they truly commute. The whole point of this theorem is that the dependence of delta in epsilon is independent of n. You know, for one group, like Sn, this is not a problem, you know, it can always move. But it's in a way independent. Now, what is the metric? The metric is the normalized Hamming distance, namely the distance between two permutation is 1 over n, the number of I between 1 to n, such that they differ from each other, right? It's kind of the natural norm. This is a bi-invariant, sorry, not norm. It's a bi-invariant metric on the symmetric group. Now, this is a lovely theorem, which is inspired by a long tradition in mathematical physics. In mathematical physics, what happens, people looked, those of you who knows a little bit of physics, not including myself, but I know enough to understand why this problem is somehow natural for them, in mathematical physics, may look at the following problem. Assume A and B are two n by n complex matrices, and you can assume they satisfy some property P, for example, self-adjoint matrices, unitary complex matrices. But if you don't want to assume, don't assume anything. Assume they are almost commute. What does it mean, almost commute? That B is close to BA. AB minus BA is nearby 0. They almost commute with respect to some norm. Now, on the complex matrices, we have many different norms, but we can take Hilbert-Schmidt norm, we can take operator norm. There is the so-called P-Schachten norm for every P between 1 and infinity. So there are uncountably many different norms. And by the way, this type of question that I'm going to ask is really different for every norm. It really depends very much on the norm and therefore on the metric. Anyway, now you take two matrices which almost commute in this sense. Are they nearby with respect to this norm? Can you just deform it a little bit sometimes you want just deform it a little bit. Sometimes you want to deform it and still keeping the property. Namely, you start with self-adjoint operators, then you still want the shifting to be also self-adjoint. Are they nearby matrices which truly commute? So again, you can say for every epsilon there exists delta such that blah, 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 as we said before. Now, there are many papers on this type of problems from complex matrices. And the answer, by the way, depends very much on the norm and depends very much if you insist that on the property P. For example, you may be able to correct it, but not preserving the property of being self-adjoint or things like that. There is actually, I forgot now the precise, there is actually two papers. One of them says every two nearly commuting matrices are near commuting matrices. And the other one says not every two nearly commuting matrices are near commuting matrices. And don't worry, both of them are correct, and there is no fundamental contradiction in the axioms of mathematics. One of them refers to one norm and the other refers to another norm. So the answer really depends on the norm. The paper of Gulnara and Liviu started this type of questions, maybe not started, I think there were, I'll mention, there were some also people studied it before, but it was kind of a nice thing in the context of permutation group. But let me generalize the original problem about commutators to something which is more difficult, more general, sorry. One can take other equations or even system of equations. So let's X be the variable X1 up to XD. Let R be relations. What be relation? I mean, there will be words in the free group on X1 up to XD. And before that, the example, we have X1 and X2, and we have only one equation, the commutator. And now we say that this system of equation R, the terminology is stable. If for every epsilon greater than 0, there exists delta than the 0, such that if we have a d-tuple of permutations which are almost solution to this system of equations, namely the distance from Ri of this A to the identity in this normalized Hamming matrix is less than delta, then we can deform the matrices slightly. We can deform them a little bit, less than delta, less than epsilon, sorry. Each one of them less than epsilon to a true solution. So if you have almost solutions, they are nearby true solution. Then we will call the system stable. So now you can say that the theorem from the previous slides is the statement that the commutator equation is stable. On the other hand, we'll come to that later on, and the equation I can tell you now, like xy square equal x cube y, yx cube is not stable. Why? Sum of y. How can we distinguish between a stable system of equation and non-stable? So here is a crucial, a very simple observation. The proof of it is half a page. I'm sure each one of you, if I'll give you a few minutes, will be able to figure out a proof. But it's crucial for the continuation. It said that the stability of the system of equations R depends only on the group they present and not on the system. Namely, assume you have two systems of equations like that. You have variable X and you have equations R. I can associate with them a group, right? That's what we are doing for living, right? In our community, we take a group presented by set of generators and certain relations, and we define a group. Let's say that somebody will start with another variables, not even the same number of variables, any system of variable y and any system and any system of equation s, and assume that the resulting group are isomorphic, namely these are the same group, then the system R is stable if and only if the system S is stable. So this means that the notion of stability now can be associated with the group. That we have now a well-defined notion of stability for the group gamma. Let's say for a minute that gamma is a finitely presented group. So we can define gamma is stable if and only if the presentation defining it is stable, and we don't have, and it's independent of the choice of the presentation of the group. So we have a well-defined notion of what means to for a group, for a finitely presented group at least, to be stable. And now the situation is like in Galois theory. We say that you see in Galois theory we have a polynomial with we ask, is the polynomial solvable by radical? We associate with it a group. The group is the Galois, what we nowadays call the Galois group of the polynomial, and we say the polynomial is solvable if and only if the group is solvable. So also here, the system of equations is stable if and only if the group is stable. But here comes the big difference. In Galois theory, once Abel or Galois proved this basic theorem that a polynomial is solvable if and only if the group is solvable, usually to check whether as a group is solvable is something very easy. Now, only a name that we introduce. We just call it stable, but how can we decide whether the group is stable or not? So now here is now basically the whole area is about this: develop techniques to decide, given a group, whether the group is stable or not. And what I'm going to describe to you is a bunch of results in this direction. Say sometimes it is stable, sometimes it's not stable, and I hope I will try to convince you that it really raised some interesting questions by themselves. Just before doing this, let me say that the notion of stability can be generalized to any finitely generated group. We don't need it to be finitely presented. And here is the definition, and I will leave you as an exercise to see that this definition, when implemented to finitely presented group, is completely equivalent to the stability of the finitely presented group. So we can take it as a definition for a finitely generated group, even if the group is not, in fact, for any group, even not finitely generated, even if the group is not finitely presented. So gamma is stable for a finitely presented group if and only if, or let's take it as a definition now, whenever we have a map from gamma to the symmetric group. Now a map, sequence of maps. When I say now maps, I mean functions, not homomorphisms. I just have arbitrary functions from gamma to the symmetric group of n, satisfying the following: for every g and h in gamma, the limit of dn, phi n of gh, the distance between phi n gh and phi n g, phi n h, the limit is 0. Namely, phi n are kind of asymptotically homomorphism. For every pair of elements, g and h, they are kind of, eventually they are going to be like, almost like in the limit, they are kind of homomorphism. So the phi n are not necessarily homomorphisms, and also I don't make any assumption on the rate of convergence to 0. It may depend on the pair G and H. Anyway, assume you have such almost homomorphisms. We call it, some people call it asymptotic homomorphisms. Then there exists true homomorphism psi n from gamma to the symmetric group, such that for every G in gamma, the limit when n goes to infinity of the distance between psi n and phi n of G, depending on G, is going to 0. Namely, the phi n are really just small deformations of true homomorphisms. And this is, for finitely presented group, this is equivalent for stability, but we can take it as a definition and for any homomorphism. So the basic question is, when is gamma stable? And till a few years ago, basically till the paper of Golnara and Liviu, who really, at least they influenced me a lot because they presented a lot of open problems there. Till their paper, very few examples were known to be stable. Free group are stable. Okay, that's trivial because it's an empty presentation. Glebsky and Riviera, who are responsible to this observation, proven that paper that finite groups are stable. Even this is not completely trivial. I mean, it's an exercise, but it's not complete triviality. And the paper of Golnara and Liviu show that abelian group are stable. You know, they show more than just the commutator. Whenever the group is abelian, and they presented many open problems there. Now, one of the motivation for this subject is that there is some hope that it will lead to a solution of that potentially it can lead of one of the major problem in modern geometric group theory, and this is the question whether every group is sofic. Let me explain that. I mean, I guess all of you, or most of you, have seen various different definitions of sofic groups. Sofic can be presented in several different ways, and the major open problem is, are all groups sofic, which is a famous problem of Gromov and Benji Weiss. This problem, which was asked like something 30 years ago and maybe even more, was maybe just a question of curiosity at the beginning, but it became a very important open problem because over the years, various conjecture, which were conjecture for all groups, for example, Kaplansky conjecture or other things, were proved to be true if the group is sofic. So if every group is sofic, then we would know it that the conjecture is Kaplansky conjecture is true always. So it would be nice to know, though I have to admit that because of the success of it, I think that the general feeling is that not all groups are sofics. There are various candidates that people are thinking about, but nobody managed to prove they are not sofic. And let me show a potential approach to this problem. So first of all, let me recall something that I'm sure everyone knows, but let me still put it in the way I want to put it. We all know what does it mean for a gamma to be residually finite, but let me write it in the following way, that a group gamma is residually finite if there exists a family of homomorphism to the symmetric group. Of course, we usually say to a finite group, but by Cayley theorem, I can embed a finite group into the symmetric group. If there exists a family homomorphism to the symmetric group, such that for every n, the distance from phi n of G to the identity is equal to 1 for sufficiently large n. Why so? Because I take first homomorphism to a finite group. I then embed the finite group into the symmetric group. The action of every non-trivial element on 1 up to n is without a fixed point, right? Because the action in the Cayley theorem, the group is acting on itself, so there is no fixed point. So the distance between every non-trivial element to the identity is really equal to 1. It does not agree with the identity element on no I between 1 to n. Now that's okay. It's easy to see that that's equivalent to res dually finite. On the other hand, let me give you a definition for a sofic group, which will be convenient for me to use. Gamma is sofic if and only if there exists a family of maps, not homomorphism, map to the symmetric group, such that for every G and H, the limit of phi n G, oh, it should be G here, not Y. The limit of phi n GH, the distance, sorry, between phi n GH and phi n G, phi n H is equal to 0. Namely, these are asymptotic homomorphisms, and the distance, and for every G which is not trivial, the distance is asymptotically 1. Namely, eventually you kind of separate it very far. Every G is separated from the identity. And now, here is the crucial observation that gives energy to the subject. If gamma is a sofic group, which is stable, then it must be res dually finite. Why? This is a trivial proof. Let's do it. If gamma is sofic, then there exist almost homomorphisms, as in this definition, asymptotic homomorphism. I have homomorphisms which are almost homomorphism converging to homomorphism. That's the definition of sofic. But if it's also stable, then every such homomorphism, as every such almost homomorphism, can be replaced by small deformation, can be replaced by a true homomorphism. And therefore, I will have true homomorphism with this property that converging to 1. And therefore, the group is res dually finite, but what we said up here. Okay? So that's fairly easy to see that if gamma is sofic and stable, then it is res dually finite. Now, let's say it in a different way. Is gamma is stable and not res dually finite, then it is not sofic. So this potentially gives us a method to find a non-sofic group. Find a group which is not res dually finite and still stable. So it's worthwhile to develop machinery to prove stability for groups, because then we will be able maybe to apply them to some non-res dually finite group to get non-sofic groups. At the beginning, this looks like a dream, but at least I think it gives some interest to try to prove this problem which I mentioned of Gromov and I must say that there was some successes together with few co-authors. Glebsky, which we mentioned, was one of them, and the Schifre and Andreas Thom. We managed to implement this methodology for different approximation type of question. I don't have time to talk about it. There is a famous problem that we were not able to solve, which called whether every group is hyperlinear. But there are other problems of this style, whether every group is Frobenius approximated. And there we managed to prove for the first time that there are groups which are not Frobenius approximated. In some sense, they are not sofic in the category of unitary, a unitary group with some of these matrices that I hinted about before by this methodology, namely to prove stability. But that's a subject for a different talk, so I won't talk about it. I just said that it gives some hope that maybe there is something. Anyway, before I go to the stability, I must mention some connection with computer science. A paper on this subject by Oren Becker, Jonathan Moussaieff, and mine is already on the archive, and next week it will be presented in a computer science conference in Fox by Jonathan Moussaieff. And it's one can think about the whole subject. In fact, when I saw the paper of Gulnara and Livio, what got my attention, I was interested in this computer science subject for a reason for a reason which appeared in the lecture, which I put the slides by mistake at the beginning of the hour about locally testable codes. Maybe I'll say a word about it in a second, but I want to show you that really this subject can be thought as a chapter of the subject of property testing in computer science. In a way, it's kind of a group theoretical section of that property testing. What is property testing? Property testing is the following, it's one of the deepest and most interesting areas in modern theoretical computer science, and not just theoretical. We say let A be any finite set. Usually, computer science like A to be just 0, 1, and let Pn be a subset of A to the n. And well, the subset in the case which is very interesting for them is error correcting codes. This is a code. A code is a subspace of F2 to the n. The membership of alpha in P to the n is testable. Sometimes they say, in short, that Pn is Q epsilon testable. Q is some natural number and epsilon is a small number. It is testable if there exists some epsilon. If this epsilon, this Q, and you have a random algorithm, which they call a tester, the algorithm is allowed to read only Q coordinates of a vector alpha. You take a vector alpha in A to the n, and you take a vector in A to the n, it's very large. I allow you to read only 70 bits, only 70 entries from the vector, and you have to decide, and the 70 is independent of n. It sounds ridiculous. And you have to decide whether the vector satisfies the property Pn or not. Of course, it's ridiculous because, you will take 70 bits and I will change other bits, right? And what can you get? So the story is, let's say it in a more careful way. You choose each time Q random bits, and the answer should not be exact. The algorithm should say always yes if alpha is inside Pn, and it should answer no with probability epsilon independent of n, and the Hamming distance, the normalized Hamming distance between alpha and the property. So, okay, of course, if you are close to the property, then you may make a mistake. But we want that if you are really far from the property, from the satisfying it, the algorithm will detect it. Now, if you think about it for a second, then what we are doing here is exactly this type of algorithm. Why? Maybe before saying it in general, let's go to the problem I started with of the commutator. I give you two permutations, and you remember I defined that they almost commute. What does it almost commute? The commutator is nearby one with the normalized Hamming distance. This really means that AB of I is equal of BA of I for most eyes, for 99% of the eyes, they satisfy the property. And the question was, can you make a small correct of small amount of the eyes that they truly commute? Now, I have so if the theorem of Gulnar and Livio really tells us that this problem is testable. The commuting, the set A of all pairs of commuting permutation is testable. What will be the algorithm? Choose random I and check if A B of I is equal B A of I. You read only very few bits from the definition of A. I don't have to know A and B totally. I will do it 70 times for 70 different I's. If they are 99% close, sorry, if they are very far from commute, then one of the I's will discover that A, B of I is not B, A of I. If they pass all the tests, they are really very close to commute with each other. And can they be corrected? That's a non-trivial question. And the theorem tells, yes, you can correct it to be commuting, which is exactly saying that this algorithm is tester for that problem. I just want to hint on that connection, and I will send you the paper as we wrote it now. It was really aimed at the computer science kind of community, and maybe you won't be happy with this. But you know, in these Fox and Stock conferences in the computer science, the tradition is you have a paper in the proceeding of the conference, and then you write another paper for a journal, which is usually kind of elaborated on that. We decided that to write another paper to be for our friends, namely for the computer, from the group theory. For the group theory community in the language, stressing group theory and some of the problem, and I hope that in a few weeks it will be on the archive. Okay, so here are some observations which give a little bit more energy to the subject. Stability implies testability of the set of solutions. Just what I explained by ends for the commutator, this is really in general. Take the set of solutions of the system of equations. Think of it as a set of d-tuple of permutations. And then we have an algorithm given alpha in sim to the d. Alpha is alpha 1 up to alpha d. We have d-tuple of permutation. Choose random I and check if they all satisfy. If they all satisfy, say yes. And of course, if they do satisfy, it will always succeed. And if the group is stable, it means that this algorithm will be a very good one with high probability. And I already explain it in details for the commutator. Now, little bit, now here is a warning, which is not completely trivial to see, I will mention later on. Stability is not equivalent to testability, because stability means that this type of natural algorithm will detect the equations. But maybe there are other algorithms which will do it. And in fact, we know to prove that now that testability is weaker than stability. And anyway, one can also show that testability depends only on the group presented by R and not on R. So we have a notion of stable group and we have a notion of testable groups. So groups are testable if there is an algorithm which check the presentation. So up to now, this is just a name. From now on, oh wow, took me more than expected. So maybe I will take your kindness, and maybe I'll talk a little bit more than an hour. So up to now, I made the introduction, and now I will give you a bunch of results with very little proof, but to give you a kind of survey what is going on. And it's kind of amazingly, quite a lot was developed in the last 3-4 years. As I mentioned before, till few years, till like 2017, I think we knew nothing, or maybe like only few examples, and now we have stability and instability results, etc. So anyway, what's the program? What's the question? As you can see, there are infinitely many problems here. Develop method to decide whether the group is testable, whether the group is stable, etc. So here are summary of some known results. Let's start about amenable group. So let me recall that if a finitely generated group generated by a finite set S is called amenable, if for every epsilon there exists a finite set F, which is almost invariant under pushing by the generators, namely the disjoint union, how you call it, disjoint, no, the different, the
symmetric difference.
What? The symmetric
difference.
The symmetric difference of S, F, and F is less than F. If you think about it, it's like you have a box, if you push by the generators, you don't move the box too much. Like nilpotent groups like the solvable group are amenable, and there are many amenable groups, but there are also many non-amenable groups. And in that, but now in that paper with Becker and Musayev, we are proving that every amenable group is testable. In a minute, I will show you that for amenable group, whether they are stable or not, it's extremely interesting problem, which is very delicate and quite deep. By the way, this result is also pretty deep, not our work. Our work is not deep. Our work uses deep work of Orenstein and Weiss to study actions of amenable groups, and we also use some work in computer science by two computer scientists, Ilan Newman and Scholler. I don't know to pronounce his name. Ilan Newman is an Israeli, so I know to say it. Who proved that actions of amenable group that Orenstein and Weiss proved somehow that the equivalent relation induced by action of amenable group is hyperfinite, and they proved that the hyperfinite relation is testable. So we combined two deep theorem and proved this. A much more delicate work is that's paper which already appeared by Oren Becker, who was a student of mine, now is a postdoc at Cambridge, and with Andrea Tom. This already published in the Duke Journal. We prove that a finitely generated amenable group is stable if and only if the finite index IRSs of gamma, I'll explain in a minute, are dense in the space of all IRSs. That's very interesting. This takes us to an area which was quite popular in the last 10 years in dynamic and ergodic theory of IRSs. What are IRSs? IRSs is not the American tax authority, IRS, but it's invariant random subgroups. What does it mean? You take the space of all subgroups of gamma. You think of all subgroups of gamma, sorry. You think of it just as a subset of the set of all subsets of gamma. The set of all subsets of gamma can be identified as 0, 1 to the gamma power, right? I decide on every element, are you in or not? and by what Tikhonov, this is a compact space. It's not difficult to see that if you have a subgroup, then it's closed in that topology. So the space of all subgroups as a natural topology as a compact space. An invariant random subgroup really means a probability measure on that compact set of the subgroups, which is invariant under conjugation. Example, this notion generalized the notion of a normal subgroup. Why? What is a normal subgroup of gamma? If you think about it, a normal subgroup of gamma in this language is a Dirac measure, so that the full measure is on one normal subgroup. It's invariant under that. Now, what does it mean for such IRS to be of finite index? So finite index means that the support of it is entirely on finite index subgroups. But there are many more IRSs. In fact, the space of IRSs is sit nicely in a kind of a Banach space, and it's a convex, etc. And the fundamental paper on that subject by Abert, Glasner, and Virac showed that IRSs are obtained from probability measure preserving action or probability space, and it's if and only for every IRS you have such a map. I won't go to that. I just say that there is a lot of research in this direction, and suddenly it came to us naturally. I have to admit, we didn't expect that. We started to these IRSs, we try elementary method, and suddenly it came upon us. And we gave a characterization in this language. You see, the space of all our IRSs is some a compact convex space in some Banach spaces. Inside, you have the finite index IRSs. And the question is whether every IRS is a limit of such IRS. That's equivalent to stability. Okay, now from this, we could answer very quickly some results of the problems of Golnara and Liviu. For example, we could prove that every nilpotent group, at the beginning, we really worked very hard. We tried to prove that the Heisenberg group is stable. And suddenly we managed by this technology to prove that every polycyclic group and virtually polycyclic group is stable. Before that, I want to stress, it was known that abelian groups are stable. It was known that finite groups are stable. It was not even known if abelian times finite is stable. It's still, I want to tell, even now, we don't know if stability is independent of finite index subgroups. Assume a group is stable, whether a finite index subgroup is stable or and vice versa, this is still an open problem. But we managed to prove that Baumschat's solitary group is stable. But I want to give a big warning to this community, because you may suggest all solvable are stable. No, not at all. The following group, beautiful group, which was kind of suggested by Herbert Abels in 79, at that time, he wanted to show a finitely presented group whose center is not finitely generated. I mean, that was his goal, but that group is not stable. I don't have time to explain why, but basically, it's related to the profinite topology. The fact that it has a finitely generated normal subgroup which is not closed in the profinite topology, this is enough to prove instability. Anyway, I don't want to be technical from now on. It's kind of just, I throw to you quite a lot of results without proof, just to show you that this area became pretty rich with interesting problem. And here is a major problem which is still open, characterize which solvable group are stable. We don't know. Even this we don't know, whether all meta-abelian groups are stable. In a minute, I will tell you we know to prove, but with a non-trivial proof that the Lamplater group are stable. and many other meta-abelian, but we don't know for general meta-abelian. We even don't know for free meta-abelian group on T generators, whether it's stable or not. Now, why this is I think it will be fascinating question to prove this. Why? Especially if you will prove it using other criterion of IRS. Why? Because think about it. If somebody come and prove that all meta-abelian groups are stable, because we know that every meta-abelian group is sofic, is amenable, that's solvable and therefore amenable. It's well known that every amenable is sofic. I forgot to say that sofic was invented by Gromov as a common generalization of amenable groups and residually finite groups. So every amenable group is sofic. So if you prove that every meta-abelian group is stable, in particular, it implies that it's residually finite. Now we know that all meta-abelian groups are residually finite. This is an old theorem of all. Now the old theorem of all was proved. It's a very beautiful theorem. It's a very beautiful proof because the proof is also not kind of a pure group theoretic. The proof, you think of the commutator subgroup of the meta-abelian group as a module for the commutator quotient. The commutator quotient is a finitely generated abelian ring, which is Noetherian. So you think of it as a module over a Noetherian ring, and you use methods of commutative algebra to prove that every group like that is meta-abelian. Now, what we are kind of suggesting an approach based on dynamic and ergodic theory to prove a very strong version of this classical theorem of all. We believe that every meta-abelian group is stable, but as I said, we don't know to prove it. We prove, this is a joint work with Aryeh Levit. We prove, it also just appeared recently, we proved that the Lamplighter group are stable. But this was it was like 30 pages paper, which used some work of Elon Lindenstrauss and Benji Weiss. You know, it was somehow we don't know. I mean, even for such simple kind of group to decide on its stability is non-trivial. And as I said, it's still open for free meta-abelian group. Now, interestingly, you know, Lamplighter groups are not finitely presented. And in fact, our work gave first example of non-finitely presented, but essentially at the same time, Zheng from San Diego also proved that the Grigorchuk group are stable. It's kind of interesting. He was interested in the IRSs. He was not interested in stability. In fact, I think in the first version he put on the archive, he said he wanted to classify the IRSs of the Grigorchuk groups, but then he realized that his classification gives that criterion that finite index are dense, and then he said, I can prove it's stable. And then we said, oh, great, there are more groups now which are known to be stable. And then he continued, and we continued, and we showed that there exist uncountably many stable groups. So if few years ago there were only very few stable groups, now we have uncountably many. The method of our method and his method are completely different. He produced many branch groups. You know, the generalization of Grigorchuk group, the rational branch group, he showed that many branch groups, uncountably many branch groups are stable. We went, that's kind of cute. I kind of like it because I feel here I mentioned something because I want to make a triumph to, you know, after I mention all, I will mention B.H. Neumann. B.H. Neumann in 1937 wanted to prove that there are uncountably many finitely generated groups. Of course, all of us know it by now, but this was the first proof. He showed, he said, look at the product of the symmetric group, the overall n, and look at the group generated by tau and sigma. What is tau? Tau is just 1, 2 in every coordinate. And sigma is the full cycle in the n coordinate. And he showed that if you take subset of the integers, you get different groups. So you have uncountably many, because for every subset of the natural number, of every subset m, you define this group GM, and they are all different than each other. So you have uncountably many two-generated groups. In 1993, in a joint work with Benji Weiss, we proved that all of them are amenable. We were interested at that time in this because of questions on expanders graph that I won't talk about. But now with Ariel Levit, we show that they all satisfy. They all satisfy the condition from the previous slide, the condition for my paper with Oren, Becker, and Tom, the condition that the IRSs are dense and therefore they are all stable. So now we go back to the masters, and all this group which were produced by B.H. Neumann to show there are uncountably many finitely generated groups, all of them are also stable. Okay, I'll take really just a few more minutes in my kind of survey. Let's go, in group theory, amenable group is one corner, and groups with Kazhdan property T is the kind of the other corner. Let's go to check what's going on there. So let me recall that a group gamma is a finitely generated group gamma is the Kazhdan property T. If all the non-trivial irreducible unitary representation of gamma are bounded away from the trivial representations, there is on the space of irreducible unit representations of a group, you can put a topology, and the trivial representation is an isolated point in that space of representation. That's a definition. It's a very important property of groups with a lot of applications. Now, but it's maybe less known, but there is a very simple argument which shows that if you have property T, not only the trivial representation, but every finite dimensional representation is isolated point in the space of representation. I'm going to use it in a second, so I mentioned this point. So what are group with property T? For example, SLNZ. SLNZ for n greater or equal 3, for n equal to naught. It does not have property T. But SLNZ has property T for n greater or equal 3, and more generally, all lattices in simple Lie groups of I rank, of rank greater or equal 2. In a joint work with Becker, I can't imagine, I wrote my name incorrectly. I wrote Lubotzky instead of Lubotzky. The funny thing is there is a mathematician by the name Lubotzky. At least some of his joint work was very much related to my work on expander. And many people gave me credit for his work till they discovered that this is a different person. At the end, we even have a joint paper together. So Lubotzky and Lubotzky, but here is Lubotzky, not Lubotzky. But I see that I made this Freudian mistake. Anyway, with Oren Becker, we proved that if gamma is a sofic group, for example, if it rests only finite, is sofic, every linear, we don't know it in complete generality. We know it for sofic groups. With Kazhdan property T, then it is not stable. So you see, in property T in general, work the opposite than amenable. Well, in amenable we saw sometimes stable, sometimes not. But here we know it's not that it's not stable. In particular, we answered the question which was open at the time, showing that SLNZ is not stable. And in this recent work with Oren and Musayev, we show that it is even not testable. As I said, testable is a weaker form of stability. As I mentioned before, all amenable groups are testable. Maybe I wanted to give a little indication of the proof, but as I am my time, I went over an hour, so maybe I'll skip this. If you will want to ask me about that, then I will go back. Let me give you there's something I don't want to stop without mentioning. Okay, one should see this proof for that. Okay, let me steal 5 more minutes from your time, and I'll finish in 5 minutes. Let me give you a very quick sketch of proof why SL3Z is not yes, property T and not. That's basically based on an idea of Java. Look at SL3Z. SL3Z acts, well, you have a map from SL3Z onto SL3FP. SL3FP acts double transitive on the set X. What is the set X? All pairs of one-dimensional subspaces of the three-dimensional space FP cube. Okay, so we have some action, double transitive action on SL3FP and therefore of SL3Z on some set X. It's known that if you have a double transitive action on a set, when you look at the induced unitary representation, right? Whenever you have a permutation representation on a set, we can look at the induced unitary representation. You look at all functions, or sorry, here it should be capital X, all functions from X to C, which then you get a unitary action there. And of course, this is never irreducible because the constant functions are invariant. The complement is all function with sum up to 0. And it's known that if the action is double transitive, then this is an irreducible representation. Now let me do the following cheating. I take the set X on which the group acts. Let's say that its order is n, and I drop one point of it. I just throw it away. Now what I'm getting is an almost action on the set Y, which is X minus X naught. I have an action on X. I drop a point. Now you understand I can kind of, I cheat a bit. Now it's not an homomorphism anymore. It's not an action, but it's an almost action in our definition of almost homomorphism, almost that. Now, if gamma would be stable, then it must be near an action. But near an action on the same, on Y, not on X. Because this was the definition that I can correct it with the same size. But if it will be a true action there, then I will get a unitary representation on L2 of Y, which is really nearby the representation on L2 of X in the topology of representation. But this will contradict Kashdam property T, because I told you before that Kashdam property T tells you that two finite dimensional representation cannot be nearby. So basically, this is the sketch of the proof for this case. But you see that this is a bit of a cheating, because the group indeed not stable, but it's stable if I would allow to bring this back, to bring this element back. So in that paper, we made the following definition. We said that gamma is flexible stable if every almost action, namely almost asymptotic homomorphism to the symmetric group of gamma, is near a true action to somewhat larger n. N is I allow you to enlarge n by little o of n. And now the proof does not work anymore. Maybe SLNZ is flexible stable without being stable. Now, to be honest, I don't have time to explain it. Maybe this is the correct notion and not stable. But when we made it, we just made it because it was natural, but it doesn't work. In the last few years, I will, and that will be my last slides, I will show you that there are various results maybe indicating that this is the right. And I was amazed and very pleased to see that in 2 months, there is a conference in Budapest about flexible stability of groups. I think the people there kind of believe that this is the right notion and even deserve a workshop on flexible stability. I admit that when we made it, we didn't really understand the full importance. Anyway, this is an open problem, whether SLNZ is flexible stable. The observation before I told you that if gamma is sofic and stable, then it residually finite, it's enough flexible stable. So potentially this may make it easier to get a non-sofic group. But I should also be honest with you. As of now, we don't know a single group which is flexible stable and not stable. So even though we have a lot of expectations from this notion, we don't know any group which is one and not the other. But let me still tell you a little bit about flexible stability, and that will be my last slide. Nir Lazarovich, Aryeh Levit, which I mentioned before, and Yair Minsky prove the following theorem. It's an open problem whether the surface groups are stable. But they managed to prove, again, it's a beautiful proof because it took us to a completely different area. The proof uses, covering theory from algebraic topology, very beautiful. The surface group are flexible stable, and it's still not known if they are stable. Even more exciting is the following theorem of Bowen and Bolton, who prove the following. Now listen carefully. They prove that if for some n greater or equal to 5, even for one single n, somebody will prove that SLNZ is flexible stable. This is an open problem. We know that it's not stable. But the proof, you remember, the proof was it's not stable, but it's almost like, at least the counterexample was not showing that it's not, maybe it is flexible stable. If somebody can prove that SLNZ is flexible stable, then there exists a non-sofic group. This is a smart claim. SLNZ is sofic. The non-sofic group that you will construct will not be SLNZ. It will be some kind of a amalgamation, H&N construction of SLNZ along some 2-3 subgroups of it. It's a smart, very smart proof, which give another motivation to study this stability of flexible stability, and maybe this will bring us to prove that there are non-flexible group, a non-sofic group. Let me quickly manage recent results of Aryeh Levit and Lazarovich, who prove that virtually free groups are stable. As I told you, we don't know the following open problem. Assume gamma delta is a finite index of subgroup of gamma. Is gamma stable if and only if delta stable? We don't know it in any direction. It's an open problem. So they show that at least virtually free group, of course, free groups are stable, but it's a non-trivial to prove that virtually are stable. And just to show you how delicate the issue is, Joanna recently proved that product of 2 non-abelian group is not stable. So every free group by itself is stable, but the product of them is not stable. So you see that we have sporadic techniques and methods to prove stability and instability, but we don't have as yet a comprehensive theory. We don't have as yet a comprehensive theory which give you, oh, what did I do? I did something wrong. I took it off. Okay, but I finished the talk. Thank you very much. I think, thank you for taking over your, more than I should from your time.
Thank you very much, Alex. It's questions, please.
Okay, may I ask a question?
Yeah.
Alex, when I actually attended your lecture on Italian online seminar, like ISCHE or something, and where you also discuss stability in matrix groups, and you, as you mentioned here, then the answer is very dependable on the norm. But my question is, what about the norm in symmetric group? We use only Hamming metric, yes, in this. But my point is, maybe you can choose another. You can at least think about another norm.
Do you
and maybe let me be more precise.
Yeah.
Let's take, say, the symmetric group of degree n, and the cycle inside of on this group of length n, say A, and let us take A square, the permutation, which in Hamming matrix it's very far from A, but my at least intuition of says me that the permutation A and A square is very close. Say if n is odd number, the centralizers or centralizer of A and A square is the same.
Right.
My point is, if we consider testability, if you consider the only subsets of Cartesian square of a set, of course, Hamming matrix is one thing. Is well, we should use Hamming matrix or something like that. But in symmetric group, you can also think about the another connections between permutations. Do you understand my point?
No, I understand. The question is, I tell you, at least from a technical point of view, what we need is a bi-invariant. You know, in principle, maybe you can do without this, but somehow it is used all the time that the metric is bi-invariant. Can you define? I wish, I really want to have the other, because the observation of Gillespie and Riviera does not really need this metric, and maybe there will be another metric which will be you know, a better one. I wish. I tell you what I know, an interesting metric, but not on this group, but on which is purely algebraic. You know, we are algebraists mainly, right? So we don't want maybe to we don't want to do maybe too much unitary groups or a norm. Okay, so here is a beautiful example. Take F to be any field, finite or infinite, and let's the family of groups now be GLNF. And define the matrix between two matrices, A and B, to be 1 over n, the rank of A minus B.
Yeah.
And you will see that this is a bi-invariant matrix. And one can start to develop the whole notion of stability in this world. And I think it should be done, and I hope it will be done. In fact, I suggested it to a PhD student of mine, but still, there are a lot of work to do, because you can do it in every different field, and I'm not sure what's the answer. I even don't know what to expect. Is it going to depend on the field? Is it going to depend on the characteristic? Is the theory going to be different if the field is finite or infinite? We have infinitely many open problem, uncountably many open problems here that one continue. And why I want to stress is because each one of them, the Glebsky-Riviera observation is valid. Namely, if you will prove for one non-residually finite group that it is stable in one of these cases, that it's sofic, namely approximated. Sofic will be enough if it's if you will, because if you think about it, this metric that I showed you, if you embed Sn inside GLNF, then the induced metric is really the Hamming one.
Let's see.
So every sofic group is approximated by this metric. So if you prove in one of these cases, if you prove stability for a non-residually finite group, you have a non-sofic group. So, there is the Holy Grail is waiting for us somewhere. So it's not a waste of time. And also I think I really find, sometimes people, especially I don't suggest a PhD student to go for problems. They have to go to problems that, okay, the Holy Grail may be waiting, but there is also something which is doable. And here there are a lot of, I think, extremely natural and interesting problems in this stability. And I'm kind of excited about that also because of the connection with the computer science. I didn't have a chance to talk about it, but this is very much connected with the issue of locally testable codes. And the local testable code was kind of a major open problem in error correcting code, and we managed recently to resolve it. And I can't say that I directly used it, but some of this way of thinking, group theoretical, we use group theory over there to do it. So it's kind of help to move between the two subjects.
I see.
So, but for SN, I don't have an idea. Maybe there is one.
Yeah, I see. So up to now, at least, Hamming metric is the only metric here.
But is it the only by invariant? I don't know. Maybe one.
No, I mean, which you use.
Yeah, right. But I don't know if it's the only one.
That's the question, at least. Is the only one.
Yeah, the equivalence of matrix, from my point of view, will be, of course, you can always say I will divide it by square root of n instead of dividing it by n, or I do something like that, but that's not the real different matrix is if they don't converge together to 0. That's if they converge together to 0, then just multiplying it by 2 or even by dividing it by square root of n, or that's not really different. Really different mean that it's really different in the like in the unitary group. Say the Hilbert-Schmidt norm and the operator norm are really different. They behave differently when n goes to infinity.
I see. Thank you.
Any other questions, comments? Well, then we should thank Alex again. And Ilya, maybe you want to say something about the next meeting?
Yeah. The next meeting, the 17th of February, Danzigal. I will make an announce on group platform, and I send in mailing list before one day before this talk. Okay, thank you very much for Alex. It's
thank you.
Great.
Please keep me on the mailing list of the seminar.
Okay.
Thank you.
Hi to all of you. Hi. Thank you, Misha. Things are okay in the family now?
Yeah, we are doing well. We are staying at home with COVID this week.
No, but with your father-in-law?
Yeah. Well, it's a long process, you know, but we are moving forward. All moving.
Yeah.
Thank you, Alex. Garrett, it's nice to see you. We haven't seen each other for a long time.
I